Hey everybody, it is Mr. Jukely here to take you through Unit 5, Lesson 5, possibly the shortest lesson in all of Physics 20 because you should already know everything for this unit anyways, or this lesson I should say. So this is the idea of circular motion and conservation of energy. So as we go through and as we look at this, we've been talking about uniform circular motion so far. So uniform circular motion, we know what's uniform about it is the speed doesn't change, right? That's uniform circular motion. Yes, I forgot an N in there, doesn't change, making it worse. But that is uniform circular motion. But when we have vertical circles, so say a roller coaster like we have over here, or a wrecking ball like we have over here, does the speed actually change? Like, does the roller coaster start with a large amount of kinetic energy at the bottom, and then as it moves upwards, does some of that kinetic energy turn into gravitational, but still some kinetic left over? So in other words, it slows down as it goes up the hill and up the loop-de-loop. Same thing with the pendulum. Maybe I'll scroll down to draw this one. As it swings back and forth and back and forth, it would have lots of kinetic at the bottom. And then gravitational potential at the top. So it's swinging and it's turning from gravitational into kinetic and then back up to gravitational and then back down to kinetic and then so on and so on, right? So the speed changes is what we're looking at. So if we're dealing with more real life situations, we have to kind of combine the things that we have talked about with uniform circular motion as well as the idea that things slow down as they move up hills or speed up as they fall downwards. So in other words, combine it with conservation of energy. So our entire lesson for this was just there in the last 2 minutes and 1 second. Other than that, we've got one example for you. And that's Unit 5, Lesson 5. The idea with the examples is we are going to be using the combination of conservation of energy and our ideas from circular motion, and typically we'll have to use conservation of energy to solve something so that we can solve uniform using circular motion, or we solve for something using uniform circular motion, wow, I can't speak, so that we can then use that to help us with conservation of energy. So let's look at this one and we'll see sort of which supervision wow, I cannot speak at all, which version it actually is. And yeah, we'll go through. So I have a 400 kilogram mass, so it's a pendulum bob on a 3.4 meter long pendulum. So there's the pendulum there. It's released from a height of 1.6 meters. So if it's released, I imagine that the speed at the top is going to be equal to 0. We want to determine the maximum tension. So that's where it sort of gets into our circular motion ideas. We know that maximum tension happens at the bottom, and we can start a good way to problem solve all these problems and like bigger problems especially is start with the end result, see what we need and see what we're missing for that. So I'm going to start with this idea of maximum tension happening at the bottom. So I know that the force of gravity on this pendulum is going to be acting downwards. I know that the tension force has to be upwards and bigger because if my circle kind of goes around like this, I know that the FC, so centripetal force, and also the acceleration need to be upwards. We talked about the other day what we should call positive for this. So center of the circle is always positive. So for this case, the center of the circle is up. So we're going to say up is our positive direction. So then we go through. So I know that I'm going to have to do something, afterwards. So I'm going to kind of split this down and I'm going to work on the second half first, if that makes sense, or the thing that we're finishing with first. So as I go through and as I expand this out, my goal is to figure out the tension. So I know that FC, which remembers the net force for circles, is the sum of all forces. So that's my tension force minus the force of gravity. And remember, you could do plus the negative force of gravity as well. This just builds that direction in. So if I'm looking for my tension, let's see, I'm going to rearrange FT is going to be equal to FC plus FG. So yeah, I can kind of expand on this. This is going to be M times, and I'm looking for the tension. Let's see, M times AC plus the force of gravity. And then don't forget, I have two versions of AC. So I'm going to use the version because I think the thing that I'm going to be missing in the end here, AC is V squared divided by R. It's also I'm going to move that little thing out of the way, pi squared R divided by T squared. But really, energy doesn't give me anything to do with periods, so I'm not really going to use that. But energy does give me the idea of speed and velocity, well, speed in particular for energy. So this is going to be mv squared divided by r plus fg. So if I have all of these things, I can solve for tension. The thing that's missing is I don't have the speed. Right? I have no idea what the speed is at the bottom. So in order to solve this, we have to kind of, work backwards a little bit and think about, okay, well, how can I get the speed? Well, this is just a pendulum being released from a height. We've talked a whole bunch in Unit 4 about energy changing from gravitational, EPG, at the top, and if it's a maximum height is released, there's no kinetic, so it's just gravitational. And then at the bottom, it turns into kinetic energy. So this is looking an awful lot like an ETI equals ETF problem, where the gravitational potential energy at the top is going to be equal to the kinetic energy at the bottom. Just as a quick reminder while we're thinking about this, what is the one assumption that we need to make, or the condition that needs to be met in order for ETI is equal to ETF, and in particular the kinetic at the bottom being equal to the gravitational at the top? Yes, if you say that there's no friction or that it's a conservative system, you are correct. So like Sven on this, gravitational potential energy is mgh, kinetic is 0.5 or 1/2 mv squared. We remember from the other units that, well, we don't even actually need mass for this, which makes life, we have it, but it does make life a little bit easier if we don't have to plug it in. So we rearrange and we say V is going to be equal to G times H divided by 0.5, or 2GH if you're using 1/2 instead of 0.5. And then of course we need to put that in a square root sign. So let's see, just got to plug in numbers. 9.81, be a little bit lazy with the units, times the height. So the height is 1.6 meters. And then we want to divide that by just a simple 0.5. So take a minute, plug this into your calculators. I'm going to extend that page down a little bit here. So let's see here. I've got 9.81 times 1.6 divided by 0.5. And then I'll take the square root of all of that stuff. So apparently it is going at the bottom 5.60285614 meters per second. Nice. So we just figured out the speed. And again, this is the speed at the bottom, which is where our maximum tension is happening. So I can use this on the other side to help me figure out the tension. And we've already done most of the work for the tension, right? We've thought our way through. So we said, okay, FC is FT minus FG and so on and so on. So now I just have to plug in numbers, which makes life pretty easy. The mass, I totally forget what the mass is though. 400 kilograms. 400 kilograms times the speed squared. So let's see, that is 5.6 meters per second squared. Please make sure that you have the whole unrounded number, 5.6028, blah, 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 not just 5.6 when you're plugging in your calculator, divided by the radius. So if I go back up to the diagram, in this case, the radius will be the length of the string. So 3.4 meters, so divided by 3.4 meters. And then we want to add to that our force of gravity. So force of gravity is just m times g. So the mass for 100 kilograms times 9.81 newtons per kilogram, which I didn't actually, expand up here, but at this point, you all know exactly what that is. So again, take a quick moment here to crunch some numbers, and I will do the same. $400. So I'm getting the tension as 7,617.176 newtons. That being said, that's a few too many sig digs, so we could either put it into scientific notation, or maybe we'll change it into kilonewtons just for fun. Back up to the original question. Looks like I got 3 sig digs everywhere, so I should have 3 sig digs here. So I'm going to do 7.62 times 10 to the power of 1, 2, 3 newtons, realizing that I just said I would do it in kilonewtons, 7.62 kilonewtons. So I said that I would do it and then did something completely different anyways, there you have it. Again, the whole point of this and the idea of this is combining things that you've already learned before, so there's not too much to it. You're going to be using the ideas of circular motion to help you solve for something in energy, or use the ideas that you have from energy to help you solve for something within circular motion. So there you go. You got a few practice problems to try out. Have fun. Let me know how it goes. Bye for now.